Okay, in the last class we studied about TCP. We couldn't complete the discussion, so we'll study the remaining part of TCP. We'll touch upon UDP and then study TCP attacks. Okay, that's the agenda for today. So this is what we have completed in the last class. Okay, and today we'll study the flow control, very little about it, not much. Then we'll look at TCP only very top level, and then spend time on TCP level attacks. Okay, before that I will repeat what we have studied, because TCP is most important protocol apart from, of course, IP. Okay, most of the applications use TCP today. All right. Okay, so we have seen that IP does not give any reliability. Okay, it is not designed for it, because it's designed as a simple packet transmission protocol which transfers protocol with the best effort, because that the time when it was designed, nobody knew, right, what is going to be the future of networking, and link speeds were low, links were highly erroneous at that time, about 30 years back. But the beauty of the technology is that it continued to serve the purpose, and it became most popular technology. In between, some other technologies came like ATM, frame relay, and many others, but IP survived. The beauty is that simply says that I have IP packet. It defines the format of IP packet, it defines a header, it defines what IP address should look like, and defines also how packet should be routed. Now these packets can contain anything. There is no restriction from designer's perspective that what this payload can be. It could be voice, data, file, music, your IPL matches, or whatever contents corresponding to anything. And other end, you receive the same and use the logic, application logic, and replay it. Okay, so there's the beauty, but it is not designed for security. Okay, and it's also not so secure. Inside security is not designed for confidentiality, it's not designed for integrity, it's not designed for authentication, it's not designed for availability. It's not, availability is essentially you can say reliability. Okay, so none of these features were thought of when it was designed, and that also is a weakness of IP protocol. Some may consider this a strength of IP is that it can carry anything, right? Had they designed all security levels inside, things IP might not have become so popular. All right, like your PSTN phones, etc. They are designed for security, but very restrictive in nature, right? Okay, then we looked at the concept of ports, because IP address gives address of the machine. Okay, within machine there are many browsers, many applications, right? Within a browser there are many windows. Okay, in a browser you open multiple windows, and each is communicating with different servers. Okay, so there must be way to, when the data is coming to machine, it should be routed to appropriate window. For example, there are multiple windows are there in a browser, or there may be some other application like email application. So data is just nothing but IP packet, right? That contains TCP or UDP. It has got to go to appropriate app or process, right? And that is done through ports. When you write a new application, then it will use some of the ports, okay, which are free at that point in time. Okay, all right, so we have seen that we have demultiplexing. When IP packet comes this way, it has got to go to one of the multiple processes, right? And when multiple processes are creating traffic, they have got to go on the same link, but IP packets may be different, right, for each one of these. it will go over the same wire. Okay, that's called demultiplexing. So again, ports are used to do multiplexing and demultiplexing, right? And we have seen the concept of then socket. Socket is nothing but combination of IP and port. In order to define a TCP connection, we need IP address of client machine, port number of client machine, IP address of destination machine, and port that is being used on the other hand. And of course, because ports are used for TCP and UDP, you have to also define the protocol. So these 5 things: IP address of the source machine, IP address of destination, and port address of source machine, port address of destination, and TCP/UDP defines very specific connection between two machines. All right. So we have seen that. All right. This shown here. Same thing is depicted here. Okay, and then we have seen the sockets for TCP is different from sockets for UDP. If you're interested to learn more about it, please read it from the book. Any book on networking will cover this. All right. So we have to create a socket, send and receive, and close the socket. All right. Then we started discussion about, once we learned about multiplexing, demultiplexing, we started learning about TCP. Okay. All right. The TCP, transport layer. Transport layer is basically two popular protocols at this level are TCP and UDP. But there are many others, right? But TCP, UDP are most commonly used. Okay, and then so only common thing about this is that they provide end-to-end service and both use ports for multiplexing, demultiplexing, right? Okay. Now, application need not to worry about how to create IP packets, etc., right? An application has just the data to send. It can create data either as a byte stream of bytes, okay, or it can create as a block of data. Okay? All right. So TCP is based on byte stream model, and UDP is based on the other model. All right. Okay, all right. So what happens is that TCP data comes from application. It goes into as a stream. It goes into a buffer, and then from that part of that data is taken and put inside a TCP packet. And then appropriate source and destination headers are added, and few other control fields are added and sent to next layer, which is IP layer. IP layer puts its header and then send it to data link layer, and then it goes from one hop to another hop. Okay, all right. So we have seen all that. Okay, the TCP says that everything in between is unreliable, and we have to just create reliable service over unreliable network. When we say reliable service, then we'll have to think of many things, right? I mean, packets loss must be recovered. So packets can be dropped by IP, right? So it has to recover from packet loss. Then out of sequence packets may arrive because IP does not say packets will arrive in order, so sequencing of packet is required. All right. Okay. All right. So these points we have seen, right? All right. Now, then we have seen that it provides, of course, reliability, ordering of packet, and byte stream abstraction. Okay. And TCP node is point-to-point network between two endpoints. TCP will run. TCP will not run on intermittent routers. The routers in between will only look at IP because their role is only to route the packet. They will look at only IP address. Beyond IP packet, I mean, it may contain TCP, IP packet may contain, that is not its role. Router will not look at what is inside. It just looks at IP header and pushes it to some next node, right? Okay, is a full duplex. It means that between A and B, data will communicate both ends. It cannot be one way. Why it can't be one way? Because it's a byte stream. It A sends to B byte stream, B receives the byte stream, and if something is dropped in between, then B will request resend it. So it means that data has to go, this request data or control data has got to go from B to A as well, right? So it's a full duplex. Okay. And then cumulative X, right? Your mother is sending 5 packets of sweets. Now you have option of calling her after you receive each packet, or you have option of calling after receiving maybe some number of packets, right? When you say acknowledgement at box number 3, that means that box number 1, 2 have already been received. That's how TCP works. Okay. Pipelining is that, okay, when your mother is sending 10 boxes full sweets by courier, she will not wait for the second box to, she will not hold the second box until she receives acknowledgement for first box. Okay, when you receive it, call her that I have received. Then if she sends second, then it's not efficient protocol. She can send all 10 one after other, and you will acknowledge from other end, right? Okay, similarly TCP does not wait for acknowledgement, but it can cumulatively send acknowledgements. And lastly, we say is a connection oriented. It means that, see, both ends have some information, right? Like sender, like your mother and you are receiving packets, she is sending packets, she will pack, she she has a connection only with you, right? Okay, and you are very well defined with your port number or whatever, and she will send first box to you, that she knows she has sent first box. Okay, and you are ready to receive it, you received it first box, right? Then you'll send ECK for first box, and then she receives the ECK and sends the second box and third box and so on, right? So there is a understanding between the two, and you are maintaining, and she is also maintaining some information. That's called connection oriented. Okay, so there is handshaking between you and your mother. Similarly, handshaking between TCP client and TCP server, or this is, okay, a server and client both are using TCP. Flow control, where your mother is sending boxes of sweets because mother is full of love for you, right? They will think that IIT Mandi does not provide great food, although she may not know that you are becoming obese here. But after receiving a one box, you have not consumed first box, and then you have received second box. Okay, then she has sent third box. Then you'll say, what you'll say? Look, I have got enough. Don't send more. Okay, I cannot consume it. I cannot keep it. I don't have space. Similarly, server or receiver, when your machine is sending packets to a server and sending it very fast pace, server will say, look, stop, reduce. I cannot handle so much, right? That's called flow control. Okay. Any question up to this point? No? It's monologue.
No, sir.
Okay, all right. Let's move on then. Okay. Of course, application we have seen, and this concept shows that if your mother is here, you are at here, and she says one box, and you say, okay, I received it. And then she will send second. Once she received this X, she sends second box. This is called stop and wait protocol. Other protocol is she continuously send packets. Okay, and you receive it. Whenever you receive, you just send ECK. Okay, this is called pipelined operation. She is not waiting for your acknowledgement. She will send one after the. So no, this is done in network because if you do this way, then it's very slow operation. Okay, because a lot of bandwidth is available, right? And you are unnecessarily wasting the bandwidth. You continuously send, and whenever receiver receives, it will act it. If it doesn't receive, it will continue act for the previous one it has received, right? So very simple protocol. This concept we have studied. How does it happen is that in byte stream abstraction, we have seen that sender sends a stream of bytes. Okay, a byte is of course 8 bits, and this guy receives it. It's like milk flowing or water flowing in the pipe, right? Okay. Now, but it's not that simple. It has to, sender has a buffer, and where sending process will keep this byte streams, and if this is the first byte, then it will go into a segment. Segment is something that goes as a part of TCP payload. This is TCP payload, right? Okay. Now note that this TCP packet size is not fixed. So now there are two ways, right? TCP will say, okay, this is my area available. I will wait for this area to get filled in. Then I will send. Other approach is that it's like truck going from one place to another. It will say, all right, until truck is full, it will not go. The second approach is that why wait? Because application on the other hand is waiting for all the stuff, all the bits. Then just send it as after some time. So TCP, that's the reason TCP packet is never fixed, right? But anyway, the part of that data that goes in TCP, we call it segment. Segment reaches to other end, mistake, and then same thing is done, that byte stream is formed and passed on to receiver, right? Now what happens, that various question, what happens if something is lost? Happens when few bytes are lost. How do you know about bytes being lost, right? Okay, all that things are important, and then we have to work on that, right? So now the byte stream model says that application generates stream of bytes. It uses TCP, so these bytes go as a payload of TCP packet. It goes to IP. So whole TCP packet goes into IP packet. So IP packet is formed. Okay, so this is the IP packet, payload of IP, and this IP header, it goes to other end over Ethernet, whatever, and finally these bytes are delivered. And this is the abstract view of what happens, right, from sender to receiver. And in fact, part of this goes here. It's like this goes the TCP data, and then header is added, it goes to other end, but this part is taken out and delivered to host. Simple. So we call this part is segment that comes from app, then TCP header is added, then it goes inside IP packet. IP is data, then IP header is added, it goes to other end. Simple. Okay, and this one we have seen. Note that here there is something called receiver window. This is for the flow control. Okay, like when you're receiving laddu, sweet packets, you will say, reduce the speed, right? So I have capacity only for 3, for example, or 2 or 1, and you will put the number here, and then when mother sees it, she will reduce the rate at which she will send you sweets. Okay, all right, very simple. Okay, now this is where we were, right, last class. Okay, now what will happen is that this is the data stream that is going from one application to another. So TCP views data is unstructured. There's no structure in it, right? It's a stream of data, but it has to create some structure because it has to send this to TCP. Okay, so it decides on the segment size. Okay, and then these segments are not numbered like this. The first segment, it won't say number 1 or number 2 segment and so on. It looks at the first byte of the segment. All right. So if file size is or it's called sequence number. Okay. Okay. The file size is 50,000, 500,000 bytes, and segment size is 100. The first byte of data is numbered 0. So this is sequence number 0. All right. and this one here is sequence number, second segment, first byte sequence number 1000. All right, and so on. So note that here bytes are numbered. Okay, now all right, and this sequence number, starting sequence number, okay, like if the second segment is going in TCP, it will insert in the sequence number field this one 1000. If first segment is going, it will insert 0, and so on, right? This is how it happens. Okay, now what may happen is that now if Mallory in between knows the first segment starts with 0, and then if she is trying to spoof this and insert spurious or some her own bits in the connection, then she knows that TCP connection is started and this is a sequence number start with 0. That's the reason sequence number we never start with 0 is called start with some number which is randomly picked up. Okay, is called ISN, initial sequence number. Okay, all right. So now if the messages are going from Alice to Bob and say she says hello server, okay, this is a message, this will go into TCP as a segment, then this initial sequence number, for example, here is 50. Then TCP, in the TCP header, if wherever the sequence field is, we'll say 50. Okay, all right. Okay. So this is so when this segment is being sent, or ISN, initial sequence number is this one ISN, and this was the first segment, this is the second segment. So second segment starts with after k bytes, then we'll say that ISN or starting or the sequence number for this is ISN plus k. ISN is initial sequence number. Now ISN is for a session. Okay, it may consist of sending multiple such segments, right? For every session, whenever you start TCP session, a random ISN number is chosen. All right, any question? All right. So this sequence number, if you look at TCP header, this of course is data. The TCP header, you will have sequence number, which contains this at number of or is nothing but sequence number, which we discussed just now. Yeah, all right. Now for here you can get the same thing. That let's assume that okay, let me just expand data. Okay, so these are the, as part of stream, these green ones are Aug has received, so you don't care about it, right? These are the ones where these have been sent but acknowledged and has not come. Okay, and these are the ones that is to be sent. Blue ones are to be sent, right? Okay, now the sequence, the window size, of course, this. Okay, because now this is the maximum number of packets you can receive when your mother is sending data, right? Okay, now this for this acknowledgement has not come, so window will not move now. So now the ISN, so sorry, the sequence number will be this, because you have to send this now. All right, all right. And acknowledge, you note that there is something called acknowledgement field also in TCP that will give the acknowledgement of the one here. It basically says that now I am expecting the next number. It has received all green ones. The last number plus 1 is the something that's expecting now. Okay, that's the theory. Okay, okay. So the sender sends a packet and data starts with sequence number X, and packet contains B bytes, so it will be X, X plus 1, X plus 2 up to X plus B minus 1. All right. Now when it is received, the receiver will send acknowledgement. All right. So now when it has not necessarily it will acknowledgement for the last byte it has received. Up to what bytes it has received properly, it will send the acknowledgement. Okay, right? So if it has received in order received bytes up to y, byte number y, then it will send acknowledgement as y plus 1. It means that everything before this has been received. Okay. So normally what happens, if sequence number is x, length of the segment is b, it will send receiver will send acknowledgement for x plus b. Okay, if the initial sequence number for sender is x plus b and length of the segment is b, then receiver, if receives properly, will send x for x plus b and so on and so forth, right? All right. And apart from that, there are TCP flags. Okay, they are basically when we say that this TCP packet is also informed, apart from sending data, let's assume that Bob is sending it to Alice. It can also say that I have received something. Like if this egg bit here is set, then it can say, yes, I have received something, and then it will tell what all it has received, right? Okay. Okay, all right. Yeah. Then there is second flag is called SYN. If this flag is set, it means that this packet is used for starting a connection. When two ends want to finish the communication and say that let's now close, this flag is called Fin's flag is set. Okay. And then similarly, suppose power goes off or something happens, and any machine can say, okay, immediately let's break the connection. Then it's called RST. Okay, I would like you to go through it, reading more about it from the book. Okay. So TCP connection is basically three-way handshaking. So, and then is TCP connection, for example, is created between IP machine at IP address A, TCP port 1 to destination machine which has IP address IPB and TCP port B. So now we'll have to create first connection, then send the data and then close the connection. Okay. So it's something like this. The client chooses a sequence number X, which is a random number. Okay, now because it's starting a connection. Then it sends SYN or synchronize packet to server. This is the client, the server, it sends a SYN packet. It essentially means what? This flag is set here. Okay. Okay, and then it defines a sequence number X. Where is the sequence number flag? This one. It sets this one as X. Server will receive this. It knows that the client is trying to establish a connection. Okay, it will respond back. Okay, I am ready to accept the connection. It will respond back with SYNAC. Okay, SYNAC is another field here. Okay, in TCP, one of the okay, just a minute. Okay, SYN flag is set with, and also X is also set. Yeah, just a minute. There's some. Okay, both SYN and ACK flags will be set. Okay. Okay, it sends back SYN-ACK, and then it also randomly selects a starting connection, because between the two and one connection this way, another connection is other way, right? So it will also choose its initial sequence number Y, and now it acknowledges that has received sequence number X and says that ACK is for X plus 1. It means that now I am expecting a packet coming from x plus 1. Okay, and then when client receive this, it will send ACK that now, okay, of course I accept your sequence number. The next packet I will receive will be y plus 1, and I thank for accepting the sequence number, my sequence number. So next packet that I will send, the first byte will have number x plus 1. Okay, this is how it is. Any question? Now the connection is established. It's like, you and your mother. This is you it's your mother, and you said, okay mom, send me sweets. Okay, and my number right now is, say, 3. Sequence number is 3. She'll say, okay fine, now the packet I will receive will be packet number 4, or sorry, byte number 4. Okay, x plus 1, and my number is, say, 10. Okay, then you will send, okay fine, I am acknowledging that. Now please start sending something from number y plus 1 or 11, and so on, right? So this is how it works, and then data transmission can start. Okay, any question? Okay, so these are details, you can look at it. Okay, now what will happen once this connection is done? Okay, first phase was connection setup that we have seen, right, in previous slide. Now data communication starts. Let's look at it in detail. Okay, so what will the first one? Client will send a data whose length is a, is a segment, data segment with length a. It means the a bytes are there. Okay, and then its initial sequence number, the first byte will have address, because we agreed for x is initial sequence number. Its sequence number is x plus 1. So this byte has sequence number. This stream is starting, or this segment is starting with number x plus 1. This byte has number x plus 1, and it is acknowledging y plus 1. Now you send something, server will start sending from y plus 1 onwards, right? Okay, because A is sending segments in this direction, B is sending, or server is sending segments in other direction. So now this server will send a data with segment size of B, and initial number of that is y plus 1. Okay, its size is, of course, b bytes. Okay, all right, and it is echoing what? X plus 1 plus a, because it has received all this correctly, and it's echoing for x plus 1 plus a bytes, right? Okay, and so on and so forth. So this way, now it will send another set of packet, another segment with size data length c, and it will act for, it has received this segment from here, the act number is y plus 1 plus b, and then so it's echoing for that, and so on, right? So in this way it will go on. Okay, and if something is lost in between, if something is lost, then the recipient will not send act for the last received one. Okay, because something in between is lost. Okay, so if server does not receive the ACK, although it has sent the data, so it can find out that I am receiving ACK for previously sent byte. So then server will send bytes from the last correctly sent byte as per receiver onwards. Okay, all right. So there are various scenarios here, and you can read it from the book, right? At the end, when your TCP session between you and server, your machine and server is end, then there are two ways to close the connection. One is using fin, when fin flag is set, Okay, and second is by immediately if connection is to be aborted, then RST flag is to be set. So it will immediately reset the packet connection. Okay, just a minute. Okay, any question up to this point? Flow control we have already discussed, that sliding window we use here, because in TCP segment there is something called window field, RW something. Okay, like your mother you will say, okay, I can receive only 4 packets at a time. Okay, so and then you can either side can change the window size depending on how much space they have, how much they can consume. Okay, all right. So it's like this, that there is a window size here, like it's shown here for receiver or server. This is say A and this is B, or client and server, whatever you can think of. So there is always a window size both machines can communicate to each other, right? So for example, when this is the data stream, when acknowledgement comes, is echoing up to this point. It means that now all this has been received correctly. Okay. Then there is sequence number, which is the next byte that I am going to send. So it corresponds to something here. Okay. So this packet A has sent this packet, means that now this up to this point it has been sent. Okay, now this has been sent but has not been acted by receiver, so this must be buffered in A until B sends the ACK for that. Okay, all right. So this is the window. It means now these bytes are to be sent now. Okay, so window always has packets that have been sent, that is not ACK or that is to be sent. Okay, as soon as ACK comes, then this window changes its position and so on and so forth, right? And there is something called window here in the packet. Okay, which says that how much can be, it defines the size of this. All right, so now sender cannot send data beyond this until it receives acknowledgement. As soon as it receives acknowledgement, this window shifts, whereas these are the byte stream. Okay, so it works something like this. Up simulation. So this is A, other is B. A has sent, okay, multiple segments. Okay, and then ACK comes. Okay, so all 3 have been received correctly. So this window shifts now. All right. Now 4th has been sent and received properly. So now window will further shift, right? But 5th has been lost in between. And then sender doesn't know the 5th has been lost, right? Okay, and it will then send 6 and 7. So you note that if you go back, note that for 6 and 7 window doesn't move, it remains the same. Okay, now from that, how does this know that A know that, you know, it has to resend packet number 5 or segment number 5? How does it know? Anybody? Because this guy will not send ACK. Okay, B will not send ACK, right? Okay, so or, okay, so what will happen as a result of that, it will again send 5, 6, 7. So look at this way. Or if B is sending ACK, then it will send ACK for previously properly received packet. Okay, here fifth is lost, so it will send ACK for up to 4. Okay, all right. So it will continue to send ACK for 4, although it has received many packet number 6 and 7. So this guy now, just a minute, will send again 5 and 6 and so on, and then it will shift its window. Okay, all right. So please go through this simulation, read about it, and you will come to know. You will learn about it, right? UDP is similar, excepting that it's not connection oriented. It's just based on datagram abstraction. The application will create a packet, kind of small segment of data. It's not a stream. It will pass on to UDP layer, and UDP layer will put this in its packet and send it across, right? So only thing UDP does is that defines ports. So that's it, right? So there is no reliability, there no ordering guarantees. Is the best effort. It's very similar to IP. It's just IP plus port numbers. That's it. So it's a very fast because there is no three-way handshake similar to TCP. Some application like video streaming application may want it. Right? Okay, attacks on UDP is very simple because there is no sequence number. So attacker just can create UDP packet. It has to know just source port, destination port, source IP number, destination IP number, and just send it. It will be accepted to other end. All right. Now next 10 minutes, let's look at what are the attacks that are possible onto TCP. Okay. The lot of attacks are possible on TCP, right? First thing first is that everything is going unencrypted, right? So this is a TCP packet. Okay, this is the header, and this is a payload. This is nothing but stream or segment, stream segment. Anybody can change data here, right? Mallory can easily change data here. So man in the middle attack is very simple. Okay. Now this, what TCP header contains, that can also be changed. Okay. So there are large number of attacks are possible. We'll study only these 3 today, so we don't have enough time. Okay, the first attack is very simple attack. It's called SYN attack. Now this thing we have already studied, three-way handshake. Okay, so what will happen is that this is a normal process. This is a client and the S is server. Client, when client wants to establish a connection, it sends SYN. And now this guy, server here, will store all the data corresponding to this, because this is a state machine. Okay, so it will store who has sent me, like all this data, like IP address of received packet, port number of received packet, destination number, destination IP number, destination port number, all this stored here in its own database or its data structure. Okay, and then send this ACK that we have seen, that we do, and this guy server will ACK it, right? Now it's a connected. All right. Now up to this point, when ACK is received, the data will remain here in this data structures, and then it will move to some other place. Okay. Now that thing where it will be for half established connection, data remains in some data structure called SYN cache, the one which we discuss here. Okay. So what will happen now? A is sending, A is a valid sender, nice person like Alice sends this SYN packet. Now all the data corresponding to this SYN packet is stored here in cache until this connection is established. So receiver will send SYN-ACK. Okay, the data will remain here in this cache. When ACK comes, now connection established. So this thing will be removed. Okay, right? Okay, all right. So you can see this, it goes like this. So this thing will remain here, information about the packet connection. Okay, and then it goes off, because this purpose of SYN cache is only for connection establishment. Once connection established, then data goes away. Now let's see the attack. This is the attacker here, Mallory. This is Alice and Bob. This SYN cache in Bob's machine. Okay, now attacker will send multiple SYN packets. Okay, let's go back. Attacker sends multiple SYN packets, it will full the buffer. Now, and it, of course, Bob's machine will send SYN-ACK, which attacker will not respond to. And possibly it has used multiple IP addresses, so this SYN-ACKs have gone to different places apart from attacker, right? So no ACK, further ACK will come from attacker. So now all this data will remain in the cache. And now a valid sender sends something, a connection request, and this ACK is full, then data is lost. Okay, now it means that valid sender cannot establish a connection. Okay, same thing is shown here. Please read through this. All right, and to counter it, there's something called SYN cookies. So it says that, okay, I am not going to have this data structures. This data set I am not having, right? So what this will contain? What it will only contain IP address of sender, port number of sender, initial sequence number, and so on, right? So it will take these information as a data. Okay, so whenever SYN request is received, it will take all this data and then hash it. Okay, and then use this as a initial and say that now, okay, this becomes your initial sequence number. That is means Alice's or attacker sequence number, whoever is trying to establish a connection. Okay, so there is no need for this cache. Okay, now when if the attacker will, of course, when receives this, it will ignore it, because it's using different IP address, or these responses may not come to attacker. But if it comes to genuine user like Alice, she will use this as an initial sequence number. So now Bob's machine will get ISN +1 as a sequence. So she can derive all these things from, like IP address, port number, etc., from ISN. Now, how does she can derive? Because the response she receives from Alice machine will, again, the packet will contain all these things: IP address, port number, and ISN +1. From this, she can Bob's machine can derive ISN, and all these things are visible, and he can do hash and compare it with this one, and if matches, then everything is all right. Okay, so in this way, DOS attack can be using SYN cookies. This attack can be taken care of. Please read through this. Second attack we'll go through in very short time. We don't have too much time. So we have seen that normal disconnection of a connection, when connection is to be deleted, normal method is sending finish packet, or with packet with finish flag. And then when final ACK comes, it means that now everything is over. It's like handshake between two. All right, you will tell your mother there's enough. Now I am anyway coming home. You stop sending sweets. She will say, okay, all right, I will not send sweets, and you'll say, okay, thank you. So that's the handshake, right? But suddenly something happens, and you say that you decide to go for holidays. Then you can say, okay, don't send anything and no other information. Okay, that's called reset. When reset flag is set, when power goes off in a machine, it will send reset before anything happens, right? All right. So that will immediately break the connection. Now attacker can now send the reset packet, which is spoofed one, to disrupt the connection. But in order to do that, it has to know the following information: source IP address, source port number, destination IP address, destination port number, and sequence number. Now destination IP and destination port is easy to guess because it knows, attacker will know where the packets are going to, and it will use most popular port numbers like port 80, etc. But source ports are difficult because it is app related, right? So it is difficult to guess. Similar source IP can be guessed. So now here it's more of a guessing game by attacker. Okay, all right. Similarly, next attack is hijacking attack, where attacker wants to put his spurious packet inside this flow of packets. It may want to insert its own packet, right? Okay, for that again it needs to know source IP address, source port number, destination IP address, destination port number, and sequence number. So again it has to guess. Okay, and then it can insert, right? So if it's not able to guess properly and it says that, okay, my initial sequence number is X plus delta, okay, and if delta is reasonable, it comes within the window, receiving window, then this will be accepted as injected data by the receiver, and then it will fill the remaining ones, which once sender sends the packets, and then it means that now this data is corrupted. All right. So now mallory can hijack the session here. All right. Okay. So there's a summary. TCP is very well designed protocol. Most of the applications use it. Okay, of course, what we have studied is very simple version of TCP, and more advanced version, more efficient versions have come in. Okay, how is little complex because the connection oriented, both ends have got to maintain the state information, and one of that is state information that receiver uses is for when connections are to be established or half established is SYN cache. And this SYN caches can be manipulated by TrueD by sending multiple connection requests such that this cache becomes full. And once this becomes full, genuine connections cannot be established, right? And then there are other attacks that we have seen using reset packet, okay, or inject the spoof the some malicious contents in between a sequence of packet. That's called TCP session hijacking. So that's all we have studied today. Any question? I know I'm going very, very fast. TCP usually may require 3-4 lectures, but I hope if you read, then you will be able to understand it fully, because we cannot understand attacks on TCP until we understand TCP. So it's kind of too much of the content. Any question? Okay, then thank you.